Welcome to Dreaming Scientist's Sleepy Stories, a place where the mysteries of the universe guide you toward peaceful sleep. Tonight, as you look toward the stars, you are not seeing the universe as it is, but as it once was. Every point of light above you is a quiet memory arriving late, drifting across a darkness so vast that time itself becomes stretched thin. And in this soft moment, you and the cosmos meet through the slow, patient travel of light. So take a breath, settle your thoughts, and let this gentle journey begin. A journey into distance, time, and the beautiful illusion our eyes knit together each night. Because the truth is simple and quietly astonishing, the sky you see is a story told long after the events have already passed. Every star, every swirling galaxy, every blurred glow in a telescope, their light left ages ago. Some lag behind by decades, others by centuries, others by millions or billions of years. Tonight, we follow that ancient light across the vast corridors of space, tracing the discoveries that revealed how deeply time and distance are intertwined. There is no metaphor here, no philosophy disguised as science, only observation, and the gentle realization that the night sky is built from echoes. Long before satellites, long before rockets, astronomers noticed something odd. Some stars brightened and dimmed ever so slightly depending on Earth's position. Others shifted by tiny angles across the seasons. These patterns refused to make sense, unless light required time to travel. To understand how this puzzle was solved, let your mind drift back to the year 1676. A Danish astronomer, Ole Romer, studied Io, a moon of Jupiter, which should have moved in a steady rhythm. Yet its timing wavered. When Earth was closer to Jupiter, the moon appeared right on cue. When Earth drifted farther, the moon arrived late. Patiently, Romer charted each pass, each delay, each shift, until a remarkable idea emerged. Light was not instantaneous. It had a speed, a finite one, and the universe revealed itself only as quickly as that speed allowed. At the time, it was a revolutionary thought. Many believed light had no travel time at all, but Romer predicted a delay of about 10 minutes, and the sky matched his prediction flawlessly. Centuries later, NASA would confirm his insight with technology he could never have imagined. During the Apollo missions, astronauts placed mirrors on the moon's surface. Scientists on Earth sent laser pulses toward them and waited for the faint return. The round trip lasted just over 2.5 seconds, a precise measure of how quickly light moves. And that same principle applies everywhere. A star 10 light-years away shows you its decade-old face. A star 100 light-years distant shows you its century-old glow. A star 1,000 light-years away reveals itself as it was when ancient cities were just beginning to rise. Let your mind wander through a few familiar names. Arcturus, 36.7 light-years away. The photons touching your eyes tonight began their journey in the late 1980s. Sirius, 8.6 light-years distant. Its light set out when many people listening now were still children. Deneb, more than 2,600 light-years away. The light you see started moving when the Roman Empire was growing across Europe. And then there is the Great Spiral of Andromeda, 2.5 million light-years away. Its soft glow left long before humans ever walked the Earth. NASA often uses these same examples to remind us that the deeper we look into space, the further back in time we travel. And when telescopes like the James Webb Space Telescope observe across unimaginable distances, the effect becomes breathtaking. JWST has captured galaxies whose light began its journey more than 12 billion years ago. Messages from a universe young, hot, and wildly creative. Astronomers built an entire history from this delayed light. Hubble's deep fields revealed thousands of galaxies scattered across a patch of sky so small it appears empty to the naked eye. JWST extends that reach even further, piercing dust, uncovering faint galaxies that older telescopes never could. Some of these early galaxies shine with surprising intensity, forcing scientists to rethink how quickly stars formed in the young universe. All of this begins with light, a traveler that carries the record of everything it touches. 1 light-year alone is nearly 9.5 trillion kilometers. The fastest spacecraft humans have ever built would need more than 60,000 years to cross that distance.
Time begins again with every eon. CCC treats the transition not as a loop, but as a geometric identification, an elegant stitching together of two eras that no longer share a common sense of scale. This idea resonates with a long tradition of questioning the nature of time. Carl Sagan once said, "We are a way for the universe to know itself." CCC echoes this sentiment, but grounds it in physics rather than metaphor. Every eon is a new instance of cosmic unfolding, shaped but not determined by the eon before it. Observations strengthen this idea. The cosmic microwave background, the CMB, mapped by NASA's WMAP and ESA's Planck mission, is astonishingly smooth. Inflation was proposed to explain this smoothness. But CCC offers another possibility. The uniformity may be inherited from the previous eon's massless, conformally smooth geometry. The tiny fluctuations we observe today, especially those JWST detects in the deep infrared, may reflect quantum irregularities seeded at the Big Bang, possibly influenced by faint geometric traces from earlier eons. Historically, the idea of conformal spacetime has deep roots. In the 1950s, mathematician Hermann Weyl explored conformal symmetry and suggested that certain laws of nature remain unchanged under rescaling. Penrose later expanded these ideas, showing that mass is the only barrier preventing spacetime from adopting conformal behavior naturally. Remove mass, and the universe becomes conformal by default. This leads to a key understanding. CCC does not claim the universe loops. It claims the universe transitions. Each eon is connected not by repetition, but by geometry. Imagine a vast sheet stretched endlessly. Now imagine shrinking that sheet into a sphere without distorting any of its angles. Conformal mapping makes this possible. CCC applies this transformation to the universe. So is space cyclic? Not in a classical sense. Its conformal structure survives. Its scale does not. Space is reborn not as a copy, but as a new manifold, shaped by the final geometry of the preceding eon. Is time cyclic? No. Each eon contains its own self-contained timeline. Do Big Bangs link mathematically? Yes, through conformal smoothing, twistor structure, and the geometry of light. These elements allow one eon's end to align seamlessly with another's beginning. And from within this picture, a quieter and more delicate question emerges at the edge of thought, one sitting at the heart of CCC's vision. If time resets with every eon, then where does life fit within the lifespan of the universe? Does life matter cosmologically? Does it play any role at all? This leads us into part 6. Does life influence the evolution or lifespan of the universe itself? Life reaches its quiet conclusion when the gradients that once fed it gently fade away, when stars dim, when worlds cool into silence, when black holes finish their long evaporation. The universe enters a stage where no structure remains capable of creating new patterns. This is not death in any biological sense. It is a soft closing of a thermodynamic story. The moment the cosmos can no longer generate novelty is the same moment it begins preparing for the conformal transition you explored earlier. What makes this connection profound is that both life and cosmology unfold through the language of entropy. Life shapes small pockets of order while increasing disorder around it. A universe that can host life is one filled with winds of energy, gravity carving pathways, heat flowing across matter, stars fusing elements into light. A universe that cannot host life is one where entropy has nearly settled, where every gradient has flattened into stillness. Life, then, is not the goal of an eon, nor its endpoint. It is a brief expression of the universe's ability to weave structure from contrast, a symptom of cosmic richness, not its definition. Yet this realization guides you to a deeper wondering. Does the appearance of life signal a turning point between chaos and form? Or is it simply one luminous chapter in a much larger thermodynamic evolution? When you look at data from ESA's Gaia mission, You see billions of stars forming, shining, cooling, and dissolving according to laws written in gravity and nuclear physics. Life arises in the middle of these cycles, shaped by them. Every test shows the same truth. Entanglement only fades when disturbed by its surroundings, through a process called decoherence. But what happens when the surroundings vanish? As the universe ages, interactions slow. Stars fade. Black holes release their final radiation. Protons may decay. Temperature differences disappear. Structure dissolves. The emptier the cosmos becomes, the fewer ways decoherence can occur. And so, surprisingly, a dying universe may protect entanglement rather than erase it. Consider the cosmic microwave background, light that has traveled nearly unchanged for 13.8 billion years. If entanglement had been present in its early state, nothing would have existed dense enough to erase it. In this sense, entanglement is fragile in crowded places, but almost eternal in empty ones. In the far future, when massless particles dominate, decoherence becomes rare. The environment becomes too thin to disrupt quantum correlations, which means the last threads binding particles and fields may outlast stars, galaxies, even matter itself. But what about the moment CCC relies on, when mass disappears? Massless particles follow paths untouched by time. Photons do not age. Their quantum states remain steady. At the conformal boundary, interactions are so weak that entanglement could become one of the final surviving features of the universe. This idea gains support when you remember how entanglement behaves around black holes. Hawking's work on the information paradox sparked decades of debate. The modern viewpoint is subtle. Information is not destroyed. It is encoded in correlations. If entanglement can persist in the intense environment near a black hole's horizon, it may also persist in the quiet, nearly interaction-free future of a dying eon. But does it cross into the next universe? To answer this, you return to the heart of CCC. When mass vanishes, the universe becomes scale-free. Distances stretch into meaninglessness. Only angles remain. Only light-like paths carry structure. Penrose's mathematics shows that these null paths map smoothly onto the early geometry of the next Big Bang. Spinorial and twistor structures may preserve directional relationships. If entanglement is encoded in phase and angular correlations, then these patterns might pass through the transition, not as particles but as relationships. This implies something bold. The last light of a dying eon may carry entanglement that seeds the earliest quantum fields of the next. History reminds us that unexpected remnants can survive cosmic transitions. When Penzias and Wilson discovered the cosmic microwave background, they were listening for noise. Instead, they found ancient photons carrying information older than any star. If thermal photons can preserve structure for billions of years, then the massless radiation at an eon's end might preserve quantum correlations far longer. The question then deepens. If entanglement persists, does it influence the next eon? CCC suggests it might, subtly, softly, invisibly, through faint biases in the earliest fluctuations of the newborn universe. These would not be memories. They would be whispers of geometry. This leads to a remarkable insight. Entanglement may be the universe's final thread, the last distinction before scale dissolves, and possibly the only quantum feature capable of bridging one eon to another. As this idea settles, another question rises gently from the horizon of thought. If entanglement can survive the end of an eon, what becomes of information itself as the universe crosses into the next? Part 8. Does information survive the boundary between eons? Here lies one of physics' hardest questions. When an eon reaches its quiet end and transitions into the next, does information accompany it? Or does the new cosmos begin with a perfectly clean slate? To explore this, you first understand what physicists mean by information. It is not metaphor. It is the arrangement of energy and fields, the measurable distinctions that determine how a system can evolve. Information is woven into atoms, photons, quantum fields, gravitational ripples, and the very shape of space-time. So when you ask whether information survives across eons, you are asking whether any of these structural differences can remain meaningful when the universe becomes massless, scale-free, and conformally smooth. This question links directly to the black hole information problem. Hawking once suggested information might vanish in black holes. Later, he revised this view, proposing that information may be encoded in correlations within Hawking radiation. LIGO's observations of black hole mergers supported this idea. Their gravitational waves carried extraordinary detail across more than 1 billion light-years. If information can survive environments that extreme, you naturally wonder, could the final radiation of a dying eon also preserve faint traces of its history? As the universe nears the conformal boundary, mass fades, interactions soften, and only massless radiation remains. Photons, gravitational waves, perhaps ultralight neutrinos. This radiation is almost uniform, but not entirely featureless. Information can hide in angular correlations, not in distances, and conformal transformations erase scale but preserve angles, which means that any information encoded in these angular relationships may pass into the next universe. To see why this matters, you return once more to the cosmic microwave background. ESA's Planck mission mapped tiny temperature variations with exquisite precision, fluctuations that trace back to the earliest moments of the cosmos. If such delicate structure can survive almost 14 billion years, it is natural to wonder whether similar patterns might also survive the soft, smooth ending of an eon. Quantum mechanics adds another piece. Fundamental laws say information cannot be destroyed. Decoherence hides it, but does not erase it. Even black hole radiation, once thought to lose information, is now understood to encode it subtly. NASA summarized this shift clearly. Black holes do not destroy information, they redistribute it. This alignment between black hole physics and CCC is striking. Both suggest that information might survive even when mass and structure dissolve. You settle into stillness, letting your breath soften as the universe quietly opens before you. Here, in this slow and gentle moment, you drift toward questions older than stars. Questions about what remains when one cosmos ends and another begins. To understand what might survive such an unimaginable transition, you turn your attention to one of the most discussed ideas within conformal cyclic cosmology, the mysterious, faintly drawn circles in the cosmic microwave background. Penrose and Gerzadian once suggested that these circles could be gentle echoes from a universe that lived before ours, ripples shaped by bursts of gravitational waves long before this eon began. Whether or not those patterns are real, the idea behind them matters. That information may cross the boundary between eons not as particles or matter, but as smooth, angle-based patterns carried by fields that no longer possess mass. And yet, you consider the opposite possibility. What if the boundary wipes everything clean? What if the universe stretches so far and becomes so uniform that all distinctions dissolve? Entropy climbing toward its final peak until every gradient fades away. A vast sea of radiation, a cosmos without memory. But even in that smoothness, something subtle resists erasure. Quantum mechanics leaves behind its faint fingerprints. The vacuum is never truly empty. Tiny fluctuations still dance in the quiet. Experiments like the Casimir effect and observations of vacuum polarization reveal that even at the lowest energies, fields hold correlations, threads of structure that refuse to be undone. If those threads cannot vanish entirely, then information cannot vanish either. It can be stretched, diluted, softened beyond recognition, but never fully erased. And this leads you to a quiet, delicate question. Does a newborn universe inherit the smallest trace of structure from the one that came before it, just enough to guide its earliest fluctuations, yet not enough to disturb the gentle smoothness required for a new beginning. Penrose once imagined that information might cross the boundary not as content, but as constraint. Not the events of the old universe, but the way its geometry was shaped at the end. The history of this idea is long and winding. In the 1970s, Hawking's early proposal of information loss in black holes was widely accepted. By the 1990s, new ideas from string theory and holography began to challenge it. In the 2000s, the ADS/CFT correspondence suggested that information could be written on boundaries rather than destroyed inside horizons, an echo of CCC's own boundary between eons. By 2019, NASA summarized this shift simply: information conservation appears to be a fundamental rule, even in spacetimes with horizons. Together, these concepts, black hole horizons, holographic surfaces, conformal mappings, paint a picture where information may be far more durable than we once imagined. CCC makes a precise claim: the transition between eons preserves conformal structure exactly. Anything based on angles, phases, or patterns of correlation can pass forward. Anything that depends on scale, atoms, molecules, biological forms cannot. Nothing is fully saved. Nothing is fully lost. Only the parts compatible with massless, scale-free geometry remain. To picture this, you imagine projecting a detailed painting onto a sphere, then gently removing every color and shadow until only its outlines remain. The picture is no longer recognizable, but it isn't gone. Only its simplest contours survive. CCC suggests that the universe performs the same act at the end of an eon. The next Big Bang inherits not the story of the old universe, but the boundaries that shaped that story. Directions without distances, phases without amplitudes, just enough to see the first quantum ripples while keeping the newborn cosmos smooth. This brings you to the central question of this chapter. Does CCC violate the principle of information conservation? Not quite. It reframes it. Information tied to mass cannot. As long as stars burn, planets cool, oceans flow, and atmospheres circulate, biological processes can thrive. But none of these gradients last forever. Stars exhaust their fuel. Planets lose heat. Galaxies grow dim. As the universe expands, energy becomes more diffuse. The great cosmic gradients flatten. To understand this decline, you look back across cosmic history. In the early universe, gradients were enormous. Matter clumped under gravity, igniting the first stars. JWST's deep images reveal galaxies shining only a few 100 million years after the Big Bang, their radiation shaping the chemistry that life would eventually depend on. Life emerges only when the universe becomes cool enough for molecules to survive, but warm enough for energy to flow. Earth entered that window about 4 billion years ago, and everything living follows from that thermodynamic opportunity. But the window is temporary. As stars burn out, fusion slows. Massive stars collapse or explode. Stars like our sun swell into red giants. White dwarfs cool across trillions of years. Black holes evaporate over timescales beyond imagination. All of this pushes the universe toward equilibrium, toward a time when gradients vanish and entropy peaks. When that happens, biology can no longer be sustained. This pattern is not speculation. It's the direct consequence of thermodynamics. Life does not end because of cosmic catastrophe. It ends because the gradients it depends on fade into stillness. Information, too, depends on energy. Every mutation, every neural pattern, every ecological shift is written using free energy. When energy becomes scarce, the creation of information slows and eventually halts. Cosmic history cannot be separated from thermodynamic history. Life begins when gradients rise. Life ends when gradients fade. And this brings you back to CCC. Does the disappearance of biological energy signal the end of an eon? Not exactly. Life ends when free energy becomes too thin to support complexity. The universe continues long past that point. gradually smoothing into a sea of massless radiation, the state required for the next conformal transition. The end of life is not the end of the universe. It is simply the point at which complexity can no longer be sustained. Black hole thermodynamics offers a striking parallel. As a black hole evaporates, it loses energy, heats up, and ends in a final burst, after which only radiation remains. Hawking described this as the evaporation of order. The universe undergoes a similar slow smoothing. Free energy becomes structure, then heat, then almost featureless radiation. Life uses the early stages. Gravity shapes the middle stages. The late universe moves towards stillness. And now, in this quiet reflection, you see what biological energy reveals. Life occupies only a brief window in the lifespan of an eon. Astrophysical data show that star formation peaked around 10 billion years ago and has been falling ever since. Long before an eon reaches its conformal end, the energy needed for life fades. Life disappears not when the universe ends, but when gradients fall too low for complexity to persist. Biological energy becomes a kind of cosmic clock, not measuring time by expansion, but by the universe's ability to support structure. And in that understanding, you rest, drifting gently into the soft, spacious quiet where questions expand like starlight and the universe breathes in long, slow cycles across unimaginable ages. When we view the cosmos this way, life is no longer something separate from astronomy or physics. It becomes a temporary phase in the universe's long thermodynamic journey. Its birth marks the rise of gradients. Its fading marks the thinning of structure. And its absence quietly foreshadows the massless, conformal future described by CCC. As this understanding settles like a soft cosmic dusk, a new question begins forming, slowly, gently, at the edge of thought. A question not about stars or biology, but about consciousness and the geometry of space-time itself. If the universe advances through eons shaped by geometry, masslessness, and information flow, then what do ideas like panentheism, panpsychism, and the nature of space-time mean beneath the lens of modern cosmology? Part 10. How do panentheism, panpsychism, and space-time fit into conformal cyclic cosmology? There comes a point when scientific questions become so sharp that they pierce straight through concepts usually considered philosophical. If space-time stretches across multiple eons, if information can travel through conformal boundaries, and if consciousness arises from physical processes tied to energy and structure, then these questions transform from speculation into scientific challenges. To explore this properly, we begin where CCC begins, with space-time itself. Einstein's field equations link mass energy with curvature, forming a living fabric that bends light, shapes galaxies, and carries gravitational waves. NASA often describes this relationship simply. Space-time tells matter how to move. Matter tells space-time how to curve. This dynamic works flawlessly within each eon. But CCC proposes something far more daring. When mass disappears at the end of an eon, space-time becomes conformal. Its scales fade away, but its angles remain. And in that moment, stripped of mass, its geometry can map directly onto the next Big Bang. This means space-time itself becomes the bridge between universes, not as a substance, but as a continuity of pure geometry. This idea has deep mathematical roots. In the 1920s, mathematicians studying Riemannian geometry discovered that certain structures remain unchanged even when distances are stretched infinitely. In the 1950s, mathematician Hermann Weyl noted that electromagnetic fields retain their structure under conformal transformations. Penrose unified these ideas through twistor theory, showing that massless, light-like structures behave beautifully when scale is removed. Under CCC, this becomes the central principle. The universe does not carry its matter into the next cycle, but it may carry its geometry. Panentheism, reinterpreted through geometry, Panentheism is often misunderstood as a spiritual concept, but scientifically, it raises a precise question. Is our universe part of a larger mathematical structure? CCC supports this, not metaphysically, but geometrically. Each eon is not isolated. It is one chapter in a vast lineage of cosmic cycles.
Interstellar space is not a simple road. A craft must navigate radiation, dust clouds, and shifting gravitational tides. Its instruments must endure decades or centuries. Its power source must persist longer than nations. Even the most advanced theoretical engines, antimatter drives, fusion reactors, beam-pushed sails, face the same obstacle, the scale of the Milky Way. This is why astronomers rely on light years. They are units of time as much as distance, reminders that information itself cannot cross space instantly. Every detail about Proxima Centauri, its flares, its planets, its magnetic storms, arrives years after the events occurred. The star may flare today. We will not see it until 4 years from now. This delay becomes another barrier to interstellar exploration. Even if a probe reached Proxima Centauri, communication would require years. 8 years for a greeting and a response. 8 years to say hello, and 8 years to hear it echoed back. Researchers studying interstellar societies emphasize this truth. Communities spread across light-year distances would be separated not by technology, but by physics. And so the central question returns: is the nearest star beyond humanity's reach? With today's technology, yes. Absolutely. Completely. But the future holds room for change. New propulsion systems are being explored: fusion targets, ion engines, ultralight sails. Astrophysicists continue studying the environment beyond the heliosphere. Each advancement moves the boundary of possibility a little farther, a little closer. Standing in this quiet place between hope and scale, you begin to sense an even deeper truth, shaped not by distance, but by the nature of light itself. Part 6. Could Betelgeuse already be gone while we still see it shining? There is a gentle, almost haunting truth in the night sky. The bright red star Betelgeuse in Orion may no longer exist in the form you see tonight. Every photon leaving that star began its journey more than 5 centuries ago. 500 years of travel through dust clouds, shifting magnetic fields, and the expanding fabric of space. The light reaching your eyes now is a message from the Renaissance, a memory of Betelgeuse as it was when early telescopes were still being imagined. Tonight, you drift toward that delayed starlight and explore why this giant star may have already met its end. Betelgeuse is a red supergiant roughly 550 light-years away, its distance refined by careful parallax measurements from Hipparcos and Gaia. That number carries a quiet implication. If the star exploded any time after the 1500s, the news has simply not arrived yet. Light needs centuries to cross the gap. Astronomers have watched Betelgeuse closely. Massive stars live quickly, burning their fuel at intense rates. When the core collapses, a supernova follows, a brilliant ending. Betelgeuse is immense. If placed at the center of our solar system, its outer layers would stretch beyond Jupiter. It is swollen, unstable, and approaching the final chapters of its life, its fate written in its size and structure. You look up and imagine a moment so bright that even daylight would not hide it. A flare in the sky so vivid that no telescope, no equipment, not even effort would be needed. Just your eyes, lifted gently toward the heavens. But the question has always drifted like a quiet riddle. When? Massive stars do not announce their final moments. They whisper them. They hint through faint shifts, changes that fade in and out like distant breaths. And Betelgeuse, it has offered many of those hints. One of its strangest chapters unfolded near the end of 2019. You might remember how stargazers, both amateurs and experts, noticed something unusual. Betelgeuse dimming far beyond what anyone expected. Within a short span, the giant star appeared to lose nearly half its brilliance. Headlines wondered if this was the beginning of its collapse, but astronomers across the world paused, measured, and looked deeper. Detailed images from the Very Large Telescope in Chile revealed a softer truth. Betelgeuse had released a massive outflow of gas, an exhalation that cooled, thickened, and transformed into a cloud of dust. That cloud drifted across our view and obscured part of the star's glowing surface. The finding changed everything. Betelgeuse was shedding material far more violently and unpredictably than anyone once believed. Then Hubble confirmed that this expelled gas raced outward at tremendous speeds, hundreds of thousands of kilometers per hour. A sign of aging, yes, but not necessarily a star collapsing this very moment. Astronomers often say Betelgeuse could explode tonight, or in 100,000 years. That enormous window isn't confusion, it's simply the nature of stars so massive that human time barely matters. And this leads to the quiet thought lingering beneath all of this: is Betelgeuse already gone? To explore that, you return to distance. 500 light-years. 500 years of delay. If Betelgeuse ended its life in the 1600s, we would only learn about it now. If it died in the 1700s, the news is still traveling. If it explodes tonight, those photons won't reach us until the 26th century. Astronomy is not only about space, it is about time stretched thin, layered across vast distances. The human mind struggles to grasp that, but science does not rely on intuition. It relies on the long, patient trail of data. And the data on Betelgeuse is deep. Infrared surveys from NASA's Spitzer telescope revealed graceful arcs of dust carved by the star's motion through interstellar gas. Radio observations from ALMA mapped turbulence in its extended atmosphere. Spectra from ground observatories traced temperature shifts glowing across its surface. Every instrument paints the same portrait: a giant in late evolution, pulsing irregularly, releasing mass, unstable but not yet collapsing. And yet, every photon you see is 5 centuries old. You never witness Betelgeuse as it is, only as it once was. Still, there is another layer to this story. If a massive star like this had exploded within the last several centuries, the blast wave should already be carving a bubble through surrounding space. It would shine in X-rays, glow in infrared, ripple with expanding shells that modern telescopes would detect. Chandra, Hubble, Spitzer, ALMA. None have found such remnants. So the evidence suggests, though cannot fully prove, that the star still lives. But the story stretches forward. Because even if Betelgeuse has not yet reached its end, we know what its final light will bring. The explosion will outshine the full moon. It will cast shadows in the night. It will linger for months in the sky. And in the heart of the fading glow, a neutron star will remain, so dense that a teaspoon of its matter would outweigh mountains. And Earth, perfectly safe. NASA repeats this with steady confidence. At 500 light-years, the supernova's power will reach us only as a soft glow, its dangerous energies long diluted across unfathomable distances. When the light does finally arrive, you will be witnessing the end of something that happened centuries earlier. That is the nature of starlight: slow, faithful, never rushed. So the question returns, gentle as before: could Betelgeuse already be gone? Yes, possibly. Nothing in our measurements rules it out completely. But nothing points to that conclusion either. Massive stars evolve on scales so vast that entire civilizations could rise and fall while their cores quietly burn, shift, and age. 500 years is a breath, a blink. Betelgeuse flickers, brightens, dims, reshapes itself as it burns through the final stages of nuclear fusion. Astronomers continue watching through every window available, from JWST's crystal-sharp infrared to Gaia's precise stellar mapping, all working within the same truth: you see the star's memory, not its present. And from that simple delay in starlight, a deeper question unfolds, one that stretches not just through stars but into human dreams of crossing the cosmic ocean. If even nearby starlight takes centuries to reach you, what would it mean for a craft trying to chase it? This leads you into the quiet, inevitable boundary. A boundary where the hope of outrunning light dissolves into the very structure of reality. Nothing with mass can ever touch the speed of light. Not because of weak engines or primitive technology, but because the universe itself is shaped around this limit. It is a law carved into the fabric of space and time. Einstein uncovered this more than a century ago, an insight echoed through every experiment, every particle accelerated, every spacecraft guided. It begins with a simple idea. As something accelerates, everything about it begins to shift. Early scientists saw this as they pushed charged particles to high speeds. Their mass-like resistance increased. Their motion refused to behave the way familiar objects do. Again and again, the same trend appeared. The faster something moved, the harder it became to push it faster. Einstein's equations explained why. Speed bends time and space. Time slows as you approach the cosmic limit. Imagine yourself aboard a spacecraft pushing toward extreme velocity. Your clock ticks normally, but compared to clocks on Earth, your time drifts, slowing gently. This isn't a sensation, it is woven into space-time itself. GPS satellites prove this daily. Their clocks drift because they move quickly and sit higher in Earth's gravitational field. Engineers must correct them constantly. Without relativity, navigation systems would fail within hours. So time dilation isn't imagination. It's science working quietly inside your phone. At high speeds, 90%, 99% of light speed, time nearly freezes. But reaching those speeds requires energy rising so sharply that intuition cannot follow. Each fraction closer demands exponentially more power. To hit the speed of light, the energy required would become infinite. And infinite energy is impossible. This is the wall. The immovable structure that locks warp drives, hyperspace jumps, and faster-than-light travel behind a boundary the universe itself enforces. Even the Large Hadron Collider, one of the most powerful machines ever built, can push particles to within a breath of light speed, but never fully reach it. The final gap is unreachable because mass increases with speed. Not in size, but in resistance. Motion becomes harder and harder, as though the particle grows heavier with every fraction gained. Light avoids this entirely. Photons have no rest mass. They are born at the cosmic speed limit and remain there forever. What about warp drives? Wormholes? Hyperspace? Theories allow spacetime to bend, stretch, and fold. But powering such distortions requires forms of energy that may not exist, quantities that could outweigh galaxies. Every serious paper runs into the same wall. Physics does not provide the fuel. And wormholes? They would collapse unless held open by exotic matter no experiment has ever found. These ideas remain beautiful dreams. But dreams with no doorway. The universe forbids faster-than-light travel because the speed of light is not just a number. It's the architecture of reality. It controls cause and effect. It defines what information can reach what event. It stitches space and time into a single fabric. Even supernova neutrinos, among the fastest particles known, never cross that barrier. When supernova 1987A erupted, neutrinos arrived before the light, but not faster than light itself. Every observation agrees, nothing outruns light through space. And as you drift deeper into this truth, you find that the boundary is not cold at all. It is simply structure, like the grain of wood, the flow of rivers, the orbit of worlds. Even if future explorers craft engines beyond anything we imagine, they will meet the same challenge long before reaching light speed. At even 10% or 20% of the limit, collisions with tiny dust grains become dangerous, releasing energy intense enough to damage or destroy entire systems. And behind every engineering hurdle stands the greatest obstacle of all, the exponential energy wall. Fusion, antimatter, beamed propulsion, each falls before that curve. And so, in this quiet moment, the truth settles softly. The speed of light is not a wall set to imprison us. It is the universe itself. A gentle, unbreakable rule shaping every star, every particle, every dream of exploration. And as you breathe slowly, you realize, understanding this limit does not close the cosmos. It opens it, revealing a universe steady, consistent, patient. One where light carries stories across centuries, and you, here on Earth, listen to them in your own time. You live in a universe that doesn't merely forbid faster-than-light travel. It shapes reality in a way that makes the idea itself dissolve. To outrun light would mean stepping outside the rules that define cause and effect. slipping beyond the structure that gives meaning to before and after. But the dreams humanity carries toward the stars do not end there. They simply bend, gently, into more patient possibilities. Quiet engines that sip fuel instead of burning it, fusion concepts still in their infancy, light sails pushed by distant beams, long-traveling probes, ships designed for centuries instead of years, and studies imagining how a person might sleep through eras. Each idea stays within the universe's quiet boundaries. Each one honors the framework Einstein revealed long ago. The faster you move, the slower your own time flows, your mass appears heavier, and the energy you need stretches toward infinity. It is not a door slamming shut. It is the universe softly explaining how its doors are built. And as this chapter settles into the faint glow of cosmic background light, your attention drifts toward something subtler, a place where time no longer behaves like a constant companion. If nothing outruns light, what happens to time when you move close to that ultimate limit? Part 8. What unfolds when time itself bends around a traveler nearing light speed? There exists a moment in physics when motion stops being simple movement and becomes something stranger, a rewriting of time. Picture a ship gliding at 99.9% the speed of light. It is not only streaking across space, it is pulling its own clock into a slower rhythm. The crew may feel only months glide by, while back on Earth, decades gently accumulate. This single idea breaks ordinary intuition and carries you straight into the heart of relativity, a place where time is flexible, personal, and never shared equally between observers. It stretches. It softens. It slows. Tonight, you drift into that stretching, into the physics that turns velocity into a quiet doorway leading into the future. Astrophysicist Kip Thorne once said that visiting the future requires only speed, and this gentle journey brings you close to why that is true. Time dilation is not speculation. It is recorded, measured, woven into the tools you use every day. Long before spacecraft reach extreme speeds, clocks reveal the bending of time. In the 1970s, atomic clocks were flown around the world. When they returned, they no longer agreed with clocks left on the ground. The traveling clocks had experienced slightly less time, not in theory, but in reality. Today, satellites orbiting Earth tick differently than clocks on the surface. Engineers constantly correct these drifted seconds. Without those corrections, GPS would wander kilometers each day. NASA explains it simply: relativity is not optional, it's required. And if time bends for satellites and jets, imagine what happens as you approach the speed of light. At 90%, 95%, 99%, the effect grows deeper. Why does time slow down? Einstein discovered something extraordinary. The speed of light, almost 300,000 kilometers per second, is the same for everyone, no matter how they move. To keep this speed constant, the universe adjusts by reshaping time itself. Fast travelers feel every heartbeat normally, but to someone far away, their entire life unfolds more slowly. At 99.9% of light speed, the differences become astonishing. 1 year inside the ship might correspond to 20 or more years on Earth. A crew could leave, age only a short while, and return to find the world transformed. Nature herself demonstrates this truth. Cosmic rays create short-lived particles called muons in Earth's upper atmosphere. They should decay long before reaching the ground. Yet thousands arrive at detectors because, traveling near light speed, their internal clocks tick more slowly. Earth receives them only because time dilates for them. No spacecraft required. Relativity plays out in the sky above you, all the time. Now imagine a future probe powered by ion engines or pushed by lasers across the dark. If it reaches even a fraction of light speed, the effect becomes profound. A few minutes or hours for the probe, months for Earth. At such speeds, a mission to a star 30 light-years away might feel like only a few years for its travelers, while centuries pass on Earth. You drift now through this idea, letting it settle like dust on a quiet window. Every process inside the ship slows in perfect harmony, its clocks, its chemistry, its biology. Travelers never notice anything unusual. Only communication reveals the truth. Messages home arrive years later, and answers lag decades behind. Extreme speed becomes a calm drift into the future. This is not fantasy. Particle accelerators record it daily. At the Large Hadron Collider, protons move so close to light speed that their internal processes nearly freeze compared to laboratory time. Physicists rely on these slowed clocks for accurate predictions. Across the universe, telescopes watch particles near black holes behaving in ways that only make sense if time has softened. Chandra detects delayed emissions. Hubble sees apparent faster-than-light motion caused by relativity's distortions. Even stars in distant galaxies show these effects in their motions. Time dilation is not rare. It is the fabric of cosmic motion. And so the meaning becomes clear. A near-light speed ship becomes a vessel that carries its passengers not just through distance, but through time. They age gently. The universe outside hurries forward. Their voyage becomes a bridge between eras separated by centuries. And as this part of the journey settles beside you peacefully, the focus shifts to something quieter, the delicate thread that tries to stretch between worlds. If a traveler drifts far into the future, what happens when they attempt to speak with a colony only a few light years away? Part 9. Why might our first interstellar settlement never truly hear our voice? Tonight, you follow a truth so subtle that it reshapes how we imagine life across the stars. No matter how advanced our technology becomes, the speed of light fixes the pace of every message we send. A transmission crossing only 4 light years takes more than 4 years to arrive. A reply takes another 4. A simple conversation becomes a decade-long exchange. Imagine yourself on a world circling Proxima Centauri. Its dim red sun spills a muted glow across thin skies. The landscape rises in quiet shapes carved by ancient geology. And far away, too far to see, Earth turns in its own distant light. If you send a message home, "We arrived. We are safe." The words begin a journey longer than childhood. They cross the new atmosphere, slip through Proxima's gravity, and enter the interstellar dark, traveling for years before touching Earth. By the time anyone reads them, Earth has changed. People aged, ideas shifted, technologies replaced. A reply begins its own slow crossing. What emerges is not conversation. It is an exchange between different moments in time. Even in our own solar system, this delay shapes missions. Commands sent to Voyager 1 require more than 22 hours to arrive. Engineers accept this easily for a robotic probe, but across 4 light years the delay becomes vast, tens of thousands of hours. Light moves fast, yet across cosmic distances, it crawls. It slows communication into geological rhythms. Signals also weaken as they spread. A beam that begins sharp and powerful becomes thin and fragile across trillions of kilometers. Only enormous telescopes can detect the faint whispers remaining. Laser beams seem promising, but they demand impossible precision. A misalignment the width of a hair could miss the entire star. Space, quietly and faithfully, makes independent worlds. A colony must solve life support, medicine, navigation, and agriculture on its own. Messages from Earth arrive too late to guide them. Even on Mars, with minute-long delays, autonomy is required. Across 4 light years, autonomy becomes identity. Knowledge diverges first. A discovery made on Proxima might reach Earth years too late for collaboration. By the time Earth responds, the colony has already moved ahead. The same happens to culture. Celebrations, customs, even language drift under a different sky. Light makes every distant world live in its own present. Earth sees the colony as it was 4 years ago. The colony sees Earth as it was 4 years ago. Neither sees the other as they are now. Distance becomes a gentle, unavoidable separation, not a wall of matter, but a wall of time. And as you rest within this quiet truth, the journey widens into something much larger. Part 10. Are we alone? Or are the stars simply too far apart to speak? The universe's silence may not be the silence of emptiness, but the silence of distance. Above you, every direction is filled with galaxies. Not hundreds, not millions, but trillions. Each holds billions of stars. Many stars hold planets. Many planets hold environments that once simmered with possibility. JWST shows this in breathtaking clarity. A patch of sky no larger than a grain of sand reveals thousands of galaxies layered across time. The cosmos is not empty. It is overflowing. Yet our instruments hear the same steady quiet: radio arrays, pulsar surveys, narrowband searches. The receivers return nothing but the soft murmur of space. This question, this mismatch between expectation and observation, is known as the Fermi paradox. Mathematically, life should be plentiful. Yet we hear no voices. Tonight, you step gently into that silence, letting science guide the way. The Milky Way stretches roughly 100,000 light-years across. Light itself needs 100,000 years to cross it. A message requires more time than civilizations usually survive. Gaia maps over 1 billion stars, showing a galaxy shaped by enormous distances, islands of starlight floating in seas of vacuum. Worlds may host life far away, but their eras may not overlap ours. Their signals, if sent, may still be traveling. Or they passed us long before we built receivers. Signals weaken over distance. Even powerful transmissions fade into background noise after only a few light years. Alien technology might use methods we have not yet imagined. Stars drift across the galaxy. A civilization close to us 1 million years ago may now reside on the opposite side of the spiral arm. Their signals could have passed Earth while we were still shaping stone tools. Life itself may be brief, a flicker on cosmic timescales. The silence does not argue for emptiness. It argues for scale. A scale defined by the speed of light. And so here you rest, looking gently across the night sky. You are not listening into emptiness. You are listening into history. Every point of light holds a story still traveling toward someone, somewhere. Our instruments grow stronger, Gaia mapping stars with incredible precision, JWST capturing ancient galaxies, radio arrays sweeping the sky for narrow signals. Each step widens our horizon. Each observation deepens the mystery. And now, in this quiet moment, you let the silence settle around you. Not as loneliness, but as a reminder of how far light must travel to let one world hear another. If this gentle drift through distance and time brought you even a moment of peace, I'm grateful you shared it here. A soft like or a quiet subscribe is always a kind encouragement as I continue creating these night-long journeys. And if you wish, I'd love to know where and when you're listening. Your reflections guide me through the next voyage. May your night be deep and restful. May peace gather around you like soft starlight. Until we meet again, on another quiet path through the universe.